Hello. So we are going to continue what we did in the last one. And when we talked about central limit theorem, we did understand that there were few parts which need to be discussed. So I will just re-quote the central limit theorem again, and in that way we can make sure that we understand. So it said that essentially xn are basically all data sets from a random sample, and what we understand is that they are IID. Also, since they are IID, what we can do is we are also given that E of xi is basically mu, while variance of xi is sigma squared. So the variance is sigma square and the mean is mu, and what we can do with it is that we are given from this statement of the central limit theorem that limit n tends to infinity, probability divided by sigma by root n less than equals to t for some real number t is equals to phi z of t, where phi z is the standard normal CDF, right? So this is basically the statement. Now try to understand this for a moment, that how we can expand this. Try to think that how we can expand e to the power minus x square here. So from Taylor series expansion, we do know that e to the power minus x square is n equals to 0 to infinity x square whole to the power n by n factorial. The prerequisite for Taylor series and this related integrations will also be embedded, so not to worry about that. Now after we have done that, we can use it inside the definition of standard normal CDF as follows. This should be x to the power 2n by n factorial dx, right? And this is how we work with it. Now what we can again do is we can write this as limit p tends to infinity 1 by root over of 2 pi summation of n equals to 0 to infinity minus p to t x to the power 2n, you can write the 1 by n factorial here, dx, and this gives you limit p tends to infinity 1 by root over of 2 pi summation of n equals to 0 to infinity and this thing becomes basically t to the power 2n plus 1 minus p whole to the power 2n plus 1, but minus 1 whole to the power 2n plus 1 is again minus, so it is basically plus p to the power 2n plus 1. So this is basically the sum we are trying to evaluate. So all in all, what we can say is the standard normal CDF can be written as follows: phi z of t is simply 1 by root over of 2 pi limit p tends to infinity summation of n equals to 0 to infinity t to the power 2n plus 1 plus p to the power 2n plus 1 divided by n factorial into 2n plus 1. So you see that this kind of definitions make sure that we are no longer in position to define all the matrices and all the corresponding definitions, but well, we get an entire series representation for the phi z of t, and what we can do is we can approximate it well if we take the first 100 terms or 1000 terms and stuff like that. So that is how basically the z-scores are calculated, and also by numerical integration as well. So this is how we deal with this stuff. Now, along with the central limit theorem, what we will also learn is the follow. So this will be learning again in the next one. This is law of large numbers. So law of large numbers is something we are going to do. So there are two versions like WLLN and SLLN, which means weak law of large numbers and strong law of large numbers, and we are going to study both of them. So attached will it be the series representations, the Taylor series, the integration prerequisite with this video as well, and in the next one we shall continue with WLLN and SLLN, and after that video we will try to do some problems on the central limit theorem and on the standard normal CDF as well. So proof 1, we are trying to prove that limit x tends to 0 ln of 1 plus x by x is equal to 1. Okay, see, this is not a very easy proof, but we can walk our way through it. I'll just show you how. Well, first of all, x tends to 0, so this obviously means that we have that mod x less than 1, since x tends to 0, so x is in the closed neighborhood of 0, right? So it's like an epsilon distance, which is very small. We can consider as small as we want to be, and it's in that distance in between 0. So basically x lies in an interval like this, where minus epsilon to plus epsilon, and epsilon is sufficiently small. Right? So with this expression in mind, what we can do is we are trying to find a series representation for logarithm of 1 plus x, natural logarithm in fact. How do we do that? Not yet, but let us try to use the theory we have used earlier, which is the Taylor series, right? But in this case we need to find it near 0, so we can use the Maclaurin series directly. We remember that Maclaurin series for fx is given by f of x is equals to summation n equals to 0 to infinity nth derivative of f at the point 0 divided by n factorial into x to the power n, right? And here we have mod x less than 1, since we are trying to find it for logarithm of 1 plus x, which is only defined for minus 1 less than x less than 1. Okay, so we need to, the only term we need to find is the nth derivative at the point 0. So let us begin and try to see what happens. So firstly, f of 0 should be ln of 1 plus 0, which is ln of 1, which is 0. So the first term is 0, like the 0th term is 0. Okay, f dashed x in fact would be 1 by 1 plus x, and this would mean f dashed 0 should be 1, right? F double dashed x would be minus 1 by 1 plus x whole squared. So f double dashed 0 should be minus 1. Again, f triple dashed x should be 2 by 1 plus x whole cube, and this would mean that f 30 is 2, right? So this is going to give us a pattern very soon if we just continue it for like 3 to 4 terms, because I do not really want to indulge you with the nth derivative formula directly, which we can calculate directly from here, but let's save that for the derivative portion. So f4 of x again would be minus 6 by 1 plus x whole to the power 4, or in other words, this is just minus 3 factorial by 1 plus x whole to the power 4. So this was give us f40 equals to minus 3 factorial. Let us do 2 more terms. f5x would then be the differentiation of this, which would give you another minus, it will make it a plus, and it will be 4 factorial by 1 by x to the power 5, which would give me f5 of 0 equals to 4 factorial. And similarly, f6 of x should be minus 5 factorial, judging by it. It should be minus 5 factorial by 1 plus x whole to the power 6, and this should be equals to minus 5 factorial, right? So as you can see, for the even order of derivative, we have a negative factorial, 1 less than it, and for the odd we have the positive factorial but 1 less than the derivative. So we can write that ln of 1 plus x, by the Maclaurin series definition, it should be f0 plus x into f dash 0 plus x square by 2 factorial into f20 plus x cube by 3 factorial into f30, and so on, right? Now once we start putting in the values, we see that f0 is 0 and f dash 0 is just 1. For the even one it's negative, if you remember, so it's not plus, it's like minus x square by 2 plus x cube by 3 factorial into 2 factorial minus x to the power 4 by 4 factorial into 3 factorial, and so on. Remembering that 3 factorial is just 3 into 2 factorial, so the 2 factorial will cut off and 3 will remain. Similarly here, 3 factorial by 4 factorial will give you a 1 by 4. Continuing in this way, we get the series as x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus x to the power 5 by 5, and so on. So this basically right here is the Taylor series expansion for log of 1 plus x at the point x equals to 0. Now we want to see that in the limiting case, we were trying to prove that limit x tends to 0, ln of 1 plus x by x, right? Now let us write it under, because the series could be a long shot. So we can use the series definition here, and we can write it as 1 by x into x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4, and so on. Now, since we know that x tends to 0 means x is not equal to 0, we can divide by x and we can find that the answer is 1 minus x by 2 plus x square by 3 minus x cube by 4, and so on, right? Now, as I know that we can always put the value of the limit whenever the function is defined, here we just have a bunch of plus and minuses, obviously infinitely many of them, but we can write this as 1 minus limit x tends to 0 and then x by 2 minus x square by 3, and so on. Okay, but all of these terms will be 0 because when you put in x equals to 0, it doesn't matter how many of them are infinitely many zeros add up to zeros only. So the answer would be just 1 minus 0, or which is 1, and thus we have proved our limit, right? A similar argument can be made for the next one, where we are trying to prove this, where we are trying to prove limit x tends to 0 e to the power x minus 1 by x equals to 1. So starting with e to the power x equals to 1 plus x square by 2 factorial plus x cube by 3 factorial, and all the way, we can see that if we just take the 1 on the left hand side and divide by x, what we get is this: 1 plus x by 2 factorial plus x square by 3 factorial plus so on. Now if you apply limit to both sides, what you get is this: you get limit x tends to 0 e to the power x minus 1 by x equals to 1, since it's a constant, plus limit x tends to 0 x by 2 factorial plus x square by 3 factorial, and so on. But then again, all of these terms are 0, so the answer should be 1 plus 0, which is 1, right? I have used this definition because I have already showed you how to get the Taylor series for e to the power x in the previous videos, so I just used the result directly. If you really want to revisit, you can just have a look at the previous videos to see how this was derived. I have done it in every step possible. That is limits. So just to recall what we did, I am going to write down all the formulas that we have revisited in the last lecture, and I also gave you proofs. I have used the Taylor series and Maclaurin series, which actually would be covered in the differentiation section, but since I have already introduced you while dealing with the probabilities, we can use it for now, but we will formally prove it in the differentiation section and use it there and know more about it in detail. But for now, actually not much of it is required in the probability course. That is why I'm skipping the details and coming to you right with the formulas and the main parts. So here is a recall of what we did in the last one, and it would be required in this section too as well. That is why it's better to write it up. So here are the 3 formulas. So these are the four formulas that we have used, right? So we are trying to actually use them in this lecture as well, because obviously we are going to introduce a bunch of new formulas in this one, which we'll be trying to understand how to do. And in this section, the new parts that we will be knowing will also be considering of obviously these four formulas, but then again the new things, the number fifth would be limit x tends to 0 sine of x divided by x, and this limit would be equal to 1. Now I will prove it obviously afterwards, but now let's just focus on the result. This result essentially tells us that the sin x function, that is the trigonometric function, it basically is equal to x if x is very small. So all of these limits, they actually give you an approximation. If you hadn't noticed, what it says is that when x is very small, what happens is e to the power x minus 1 is almost x, or in other words, e to the power x can be approximated as 1 plus x when x is very small. So x is like very small. Okay, similarly for this one, we can also say that log of 1 plus x can be directly approximated by x when x is very small. By very small I mean that x is around the range of, x is like less than or equals to 10 to the power minus 9 or something like that. And similarly here we also say that sin x is an approximation to x. Okay, or the approximation to sin x can be written as x when we have very small values of x, such as, like as I said, 10 to the power minus 9, 10 to the power minus 10, and so on. So this limit formulas also give you an approximation on what to do, and we would like to use this formula as follows. So suppose you have limit x tends to 0 sine of 2x by x. So as before I have told you in the adjustment section, we need to have a 2x in the denominator so as to adjust it. So we can write this as sine of 2x by 2x equals to 2, right? Okay, so another example would be limit x tends to 0 sine of 3x divided by sine of 2x. Now you have done one of these problems in the last video, but if we do not actually recall it, we can directly use the concept behind it. That is, what we need to do is to make this limit work, to make the sine 3x work, we need a 3x dividing it, right? So just forcefully add the 3x like this into 3x, right? And similarly for the sine 2x part, you can forcefully add the 2x and have a 2x here, right? So this should give us limit x tends to 0 sine of 3x by 3x, and as I've already said that individual limits will can be evaluated separately as long as they are existing and they're finite, like this, and multiplied by, we have another limit which is the extra 3x and 2x, like this, right? Okay, so this basically amounts to the part where we have limit x tends to 0 sine 3x by 3x will be 1, and this would be 1, and this would be 3 by 2 into 1 by 1, where this limit evaluated to 1, this limit evaluated to 1. So this would essentially give you 3 by 2. We can come to a general conclusion on this part, that whenever we are trying to evaluate a limit of this kind, this would be equal to m by n, and we can without loss of generality add the part that m by n where n is not equals to 0, right? Yeah. So this all in all is the basic fundamental difference in the whole thing. Now what we can do next is to try and prove this formula. We can prove it as follows, and then again we would again need the series definitions and everything, so I'm going to do that. This is what we need to prove, and first we are trying to find the expansion for sin x. Right. So we're trying to find the expansion for sin x, and to do that we again need to consider our Maclaurin series, which is like sine of x should be equal to n equals to 0 to infinity fn 0 by n factorial into x to the power n. In this case x belongs to R because the sin x is defined and convergent for all values of x. So here fx is obviously sin x, so here f of x equals to sin x, and we would try to find the different derivatives of this. So let us start with the first one. F of 0 is 0, right? Now f dashed x would be cos x or cosine x, and f dashed 0 would be 1. So this is a general thing that sine of 0 is 0 and cos of 0 is 1. Okay, we are just using that fact. Now the derivative of cos x again would be minus sin x, and this would give us f double dash 0 equals to 0. Then again f triple dash 0 triple dash x would be minus cos x because the derivative of sin x is just cos x, and f30 would be equal to minus 1, while f40 and minus this would be again sin x, f40 would be 0, and f5 would be same as f1. So you can see the first four coefficients are as follows. So the coefficients repeat itself and they are periodic in the order 0, 1, 0, minus 1. These are the first four coefficients and this will repeat itself, right? So in that way we can write the Taylor series for sin x as follows. Sin x would be equal to 0 plus 1x plus 0 x square by 2 factorial minus 1x cube by 3 factorial, and then again 0x to the power 4 by 4 factorial plus 1x to the power 5 by 5 factorial plus 0x to the power 6 by 6 factorial minus 1x to the power 7 by 7 factorial, and so on. Evaluating this, actually what we get is x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial, and so on. So we see only the odd powered x terms remain here, and we can write this as a series as follows. Summation n equals to 0 to infinity minus 1 whole to the power n x to the power 2n plus 1 divided by 2n plus 1 factorial. This is the Taylor series representation of sin x around 0. Now from the series itself it is quite clear that sin x upon x would be equal to 1 minus x square by 3 factorial plus x to the power 4 by 5 factorial, and so on, right? So if you had to apply limit to both sides of this equation, sine of x by x, it would be 1 minus limit x tends to 0, x square by 3 factorial minus x to the power 4 by 5 factorial, and so on. It would be 1 minus 0, or it would be 1, right? Okay. So this would give me the result that I wanted to prove, that limit x tends to 0 sin x by x is 1, and we have seen a few results where we can use it as well. Now let's do a problem. What if we had limit x tends to 0 log of 1 plus sin x by 2x? What would this limit be equal to? Now at first glance the limit looks like a much more complex version of what we have learned till date, but then again, if you remember how to adjust things, we can easily do it. Well, I'll tell you how to do that. See, this is an example where we actually have to use the fact that the limit can go inside, this limit operator can go inside. It's basically like a wall bang. You can go inside functions, you can operate on functions there and then just come back, you know. So what we try to do here is this. We will be trying to adjust every part. So we start off with the first anomaly. Obviously we needed to have log of 1 plus x, which is in the formula, which is the formula that you've learned, that log of 1 plus x whole divided by x would be 1 when x tends to 0. But instead we have a sin x, so we forcefully add a x here and multiplied by what remains is sin x by x, right? Similarly here we have 2x. Now as I said, the limit can go inside, so we can write it as limit x tends to 0, bring the half outside, log of 1 plus x into another limit here, limit x tends to 0 sin x by x, and we can apply limits to them as long as they exist. Okay, so here it does exist, so we can apply sin x by x directly and make it 1. So it will become half limit x tends to 0 log of 1 plus x into 1 here, right? Because the limit exists and sin x by x is 1. So now you see it has become a much more easier task for us because it's just the formula and we can easily see the value of it. Log of 1 plus x by x, this is 1, so the answer will be 1 by 2. So problems like this can be evaluated just using this adjustment technique, where you need to adjust every term and you need to find what corresponds this, what relates this with the formula that we were working on. If we are able to do that, I think there won't be any problem in limit that can't be solved, right? Okay, so this gives us a basic idea. Now let us do some tricky problems, starting off with the first one. As x tends to 0, right? Now the limiting value of x to the power x as x tends to 0 can be found out, and it basically is we are trying to find this thing. Let us name the limit L, and we are trying to find limit x tends to 0 x to the power x, right? So I would like you to give a thought about this, that since none of what we have studied is actually close to this problem, right? Here we are trying to find the value of x to the power x when x tends to 0, but it just seems like we are trying to find 0 to the power 0, right? So this doesn't exactly correlate with what we have done, but there is a way we can find this. and that is how we actually are trying to evaluate this limit, and that is the exact reason why I have named it as L, because otherwise I would have not needed a variable to represent the whole limit's value, but here we do. Because whenever you see this kind of exponential things which are not solvable, as I said, functions and limits are interchangeable, so we can take log on both sides to find this. So firstly it would be log of limit x tends to 0 x to the power x, right, if we just take the log of both sides, and then the limit would just come out, and what you would get is something like this, log of x to the power x, right. Now this would give you limit x tends to 0 x log x using the properties of log x, right. Now x log x can be evaluated, and it evaluates to 0 because there are multiple ways we can go about it, but right now we can just take for granted that this is 0, and since this is 0, you can think of it as this way, because x moves to 0 much faster than log x does to infinity, because remember that log of 0 is minus infinity. Okay, so this becomes log of L equals to 0, but we were interested in finding the value of L and not log of L, so L should be e to the power 0, which is 1. And it is very interesting to note that the value of x to the power x, that is what seems like 0 to the power 0, actually approaches 1, and you can check it by using smaller and smaller values of x in a scientific calculator, that this value indeed goes to 1. So that's how the beauty of limits is. You can just evaluate such a complex thing which otherwise would not be very intuitive, can be found out in a 3 to 4 steps, right. Okay, let's do some basic problems, some well-known problems and stuff like that here, and we shall do a lot of limit problems from now on to make sure that we have practiced enough. So problem 1, find the limit so this is the limit that we want to find, and let us try to find it using what we have learned. So the problems I'm going to give is not really based off on all the formulas that we have learned, because we will do problems on that once we are in the derivative section, but for now, for the general limit problems which we need to learn, because otherwise we won't be able to understand derivatives properly, and if we do not understand derivatives properly, we won't be able to understand integration at all, and through integration is the only way you can do continuous random variables and all the other stuff in probability and statistics that are in advanced level. You need to have a very good grasp of calculus. So solution for this, so note that we are trying to find this limit. We can obviously try inputting in 2, but doing so you would find that you would get a form of 0 by 0, which is very obvious because that's what you usually get. So So we will try to cancel the factor x minus 2 from numerator and denominator to get this, something like x minus 2 into some gx, and here x minus 2 into some fx. Okay, we are trying to get something like this, but how do we get that? Let us try to factorize the things first. So first of all, x square minus 4, this is just x square minus 2 square. This will become x minus 2 into x plus 2, right? Next comes x square plus x minus 6. This is just x square plus 3x minus 2x minus 6. This becomes the factorization part. Now the limit L then becomes limit x tends to 0. In the numerator we have x minus 2 into x plus 2, and the denominator we have x minus 2 into x plus 3, right? And I think the limit was x tends to 2. So this will become, after cancelling of the factors, we get limit x tends to 2 x plus 2 by x plus 3. This would give me 2 plus 2 by 2 plus 3, and this should be 4 by 5 or 0.80. This is the answer to the question, right? Okay, let us do the next one. So I hope this was clearly understandable. Problem 2. Okay, the problem 2 is something like this. Find so we are required to find the limit h tends to 0, 1 plus h whole square minus 1 whole divided by h. Okay, so we'll do it as follows. I'll just write the steps clearly. We set L equals to limit h tends to 0, 1 plus h whole squared minus 1 by h, and now we evaluate it as follows. So we use the formula. Now we broke it down, and now we can just use the ones cancel off. So it's like h into h plus 2 whole by h, and the h can cancel off because of course h tends to 0 implies that h is not equals to 0, and we are left with limit h tends to 0 h plus 2, which simply is 2, which is the answer. So these are not very hard problems. These are like the easier versions, but we will gradually move on to tad harder ones. Okay, so let's begin. Let's go. For the next problem we have limit x tends to 0, root over of x plus 2 minus root over of 2 divided by x. So now this is one of the unique problems that we have not done yet. It's a limit problem involving surds, right? So as usual, if you just put in the value of x as 0, you see that the numerator becomes just root 2 minus root 2, which is 0, and the denominator also becomes 0. So that should not do it. So instead what we can do is we can rationalize them. So whenever you have surds, remember to rationalize them. Okay, so we denote and therefore L should be equals to limit x tends to 0. It's always a good idea to like give a name or a variable representing your limit. So it's root over x plus 2 minus root 2 divided by x, and this shall give us limit x tends to 0. Now how to rationalize? You need to multiply it with the conjugate. Now here the conjugate is this portion, and the denominator would be like this. Okay, let's evaluate it. Limit x tends to 0. So it's in the form a minus b into a plus b, which we know is equal to a squared minus b squared. And whenever you have a square root and you square it, obviously the square root just gets cut off and the expression inside just comes outside. So it's basically root over of x plus 2's whole square minus root 2's whole square divided by x into square root of x plus 2 plus root 2. Do not worry about what will happen in the denominator just yet. So we should always continue doing it and the problem will solve itself. So here it becomes x plus 2 minus 2 divided by x into root over of x plus 2 plus root 2, right? Okay, this 2 and 2 will cut off and you will get x by x into root over of x plus 2 plus root 2. Now this excess in the numerator and the denominator can cut off, because obviously x tends to 0 would imply x is not equals to 0. It's a valid operation, and thus we have limit x tends to 0 1 divided by root over of x plus 2 plus root over of 2, right? And this should give me, when I put the value as root 2 plus root 2, which is 1 by 2 root 2, which is the answer to our question, right? So just to revisit, what we did here was to multiply with the conjugate. So remember this as a thumb rule. Whenever you have either in the complex number section or in this limit section involving surds, in any case, whenever you have a surd in a numerator or a denominator, you would always like to rationalize it by multiplying it with the conjugate, right? So finding a conjugate is not really the hardest thing, because if you know about surds, you know about conjugates too. It's basically a 8th or 9th standard thing. But yes, you can multiply with surds to get a lot of answers like that. Okay, so let us do another one. So problem 4 would be something like find the limit x tends to infinity e to the power x plus e to the power minus x by 2 plus e to the power x. Now this is a special limit because firstly it's an improper limit where the value of x is not really a function or a number that you have been pretty much been used with, but it rather is infinity, where you just know the notion of infinity. So here the things becomes a little bit more complex than before, but we can handle it, and I'm going to show you exactly how do we do it. So let's do it. Let us name the limit L first. So in the solution I will denote the limit by L, and we have to note a few things like e to the power x when limit x goes to infinity, and when I say infinity I mean positive infinity, honestly. So when this happens, we give the answer as plus infinity, right? But if it is like limit x tends to infinity e to the power minus x, then the answer becomes 0. Okay, so like these are some of the things that we need to understand in order to do this problem. So let's begin. L equals to limit x tends to infinity e to the power x plus e to the power minus x by 2 plus e to the power x. And what we can do is we are trying to convert them into as much e to the power minus x's as possible, and because in that way we will get a notion of 0, which is at least a number we can work with, and we cannot actually work with infinity, right? So dividing up and down by e to the power x would be something like this. And in the denominator as well, like this, right? Completing the division, we get something like this. So e to the power x by e to the power x would be 1, and this should be e to the power minus 2x. Similarly, it should be 2 e to the power minus x plus 1, right? Now, since we know x to the limit x tends to infinity, e to the power minus x is 0, and so would be e to the power minus 2x. So this would give us 1 plus 0 by 2 into 0 plus 1, or 1 by 1, or that is 1, right? So let us do another problem of the same kind. Problem 5. Find the limit s tends to infinity s to the power 4 plus s square plus 13 divided by s cube plus 8s plus 9, right? So we are trying to solve this problem, and for this video this would be the last problem. So as you can see, like this problem again has the notion to deal with infinity, and that is why we are trying to understand how to find this problem. So a possibility which we have to be open with is that in problems of improper limit, the answer may as well be positive infinity or negative infinity as well. So it is not necessary that you always have an answer which fits like the beauty of the problem, like let's say 1, 2, 0, 0.5, or a real number. It may not be that case. It may be that the answer is positive infinity, and if you're sure about it, then it is the answer. Okay, so let us try and see what this limit will be. So denote the limit by L as usual. Right, so when we have two polynomials dividing each other and the limit of the variable goes to infinity, we try to reduce the power of the highest variable. So we divide up and down by s to the power 4, because otherwise if a single part of s remains in the numerator, that would itself go to infinity, so the answer would be infinity then. So you divide by s to the power 4 to get 1 plus s to the power minus 2 plus 13 s to the power minus 4, and here you get s to the power minus 1 plus 8s to the power minus 3 plus 9s to the power minus 4. And when you put in the value, what you get is 1 plus 0 plus 3 into 0 by 0 plus 0 plus 0. But this becomes 1 by 0, which means it goes to positive infinity. Okay, so the answer is positive infinity. This is also true because the power of the the highest part of the variable in the numerator is greater than the denominator. So whenever you have something like this, I'll just write it as a thumb rule here. If fx is greater than gx and degree of fx is greater than degree of gx, then limit x tends to infinity fx by gx would be equal to sine of fx into infinity. So if it's a negative polynomial, it would be minus infinity. If it's a positive polynomial with the leading term being positive, it would be a positive infinity. But in other words, in all the cases, it would be infinity. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.